Okay, good afternoon. Let's start lecture. Okay. Okay, so let's quickly review what we did in last lecture. We started common filter design. So basically, we're talking about a system with noise, with both the so-called process noise and also the sensor noise at here. So the W vector is a sensor process noise. The vector V at here represents the measurement noise or sensor noise. And we have certain basically assumptions made, okay, for the noise. Both noise, we consider them as zero mean and white noise, basically. Okay. So the mean value for the both noise will be 0, right? At the same time, okay, we consider, because white noise, so they are independent, and we can define, okay, based on the actual noise property, we can define the covariance matrix, okay, basically the variance of noise at here, right? So that's some of the properties I listed in the previous lecture, okay? So let's continue from here. Basically, how do we design a common filter to do observation, okay, of the system states while there's noise in the system? So there's a couple properties that you just have to remember here is our W here represent the covariance matrix for the process noise, and the RV here represents the covariance matrix for the sensor noise at here. Okay. Yeah. Okay. As I said, common filter. The purpose of the common filter basically it is essentially an observer, right? A type of observer design. So you give your system U and Y and output here to the system here. We're supposed to get an estimation of the system X hat. Okay? And of course, objective is typically objective is right is X hat. Okay, go to X of K. Okay, so typically, so that objective guarantees that you have a estimation error to be 0. Okay, but however, because we're talking about it here is a stochastic process. It's a process. It's a sensor or the signal that has noise in it. So this objective is actually not achievable, okay, in this particular situation. Okay. So this is a typical objective, okay, as an observer. Okay. But for common filter, okay, the objective is not, okay, this guy here. Okay. For common filter, what we do is, okay, we want to, so the objective is to minimize, okay, the following matrix P of K plus 1 and equal to E K plus 1 and E transpose K plus 1 . The objective is to minimize this one here, and E is the estimation error. So E is the estimation error here. Okay? And the P at here, we call this is basically called the covariance of this E k plus 1 in this case. Okay, so this is basically the covariance matrix for the estimation error at here. Okay. So technically speaking, right? So technically speaking, what's really going on here? If I write it down, the full expression, basically, use a different color here. Maybe. So technically, when you define the covariance matrix for a certain random variable, so how you define is this is estimated expected value, okay, and E. Okay, at for example, it's a k plus 1, and then minus the mean value, and then multiply by, and then minus the mean value, transpose, right? So technically, the p of k plus 1 is defined as this. Okay, that's right. Yeah. So this is the original definition of a covariance matrix, right? Yeah. But what we do at it here is we're gonna assume the so-called unbiased estimation. So unbiased estimate. Unbiased estimate is a concept. It's a very simple concept. Let's say you have a statistic which is mean, right? Mu, okay? Expected value mu. So if I cannot get the actual mean value or expected value of the whole population, I could use what to estimate that mean? Exactly. I could use a sample mean, right? To estimate the population mean. So the sample mean x bar is basically the so-called unbiased estimate. So that sample mean x bar at here, right, is a good estimation of the population mean, right? So that's basically called unbiased mean. So
that occurs when you have a big enough sample?
Basically, yeah. When you have a bigger sample, you will infinitely approach to this one here, right? But the mathematical idea is essentially, if you use this as an estimator for that statistic, then this is basically the so-called unbiased estimation. So in other words, the expected value of the sample mean is what? The mu at it here, essentially. Okay. Yeah. So for our case, okay, we're assuming unbiased estimation at it here. So that essentially means the expected value of the mean value for the error should be 0. Okay. So essentially, if you think about the expected value of the error, so the more complete, equal to the mean value of the error, right? And then this equal to 0. Okay? Yeah. So the error, essentially, the estimation error basically is a distribution, right? It's a distribution, and it's a random variable, and the mean value of the error is 0, but of course you do have variance, right, associated with this error here. Okay? Yeah. So now if I expand this expression, then you'll get that expression here. Okay? Yeah. So that's how this covariance matrix is finally listed at here. Okay, so mathematically, just a side thing in here. Okay, so another thing that you should also know is, okay, minimizing p. Okay, so minimizing this p, this expression at here. Also minimize the following expression: j equal to expected value E transpose k plus 1 and the E k plus 1, like this. Also minimize this one. What's the difference between this one and this one here? Well, there's transpose here and then transpose over here, right? Yeah. But that's a fundamental difference at it here. So see, this error here is n by 1 matrix, right? And this is transposes a 1 by n. So you create actually an n by n matrix at here. Okay, that's covariance matrix, right? Yeah. But then this one here, this is 1 by n, this is n by 1. So when you multiply this together here, you get single value here. Okay? Yeah. That's the difference, right? That's the mathematical difference. And the other difference is this expression, or basically the multiplication of these two vectors that are here, will actually end up just basically become the trace for the original matrix P. Okay? Yeah. So trace linear algebra basically means the addition, the summation of all the diagonal elements. Okay, all the diagonal elements. Yeah. As a matter of fact, all the diagonal elements representing basically the variance. In this one here, this is a covariance matrix, right? Yeah. So this P matrix will be a diagonal matrix at here actually. So when you add all the diagonal elements up, that's essentially adding up all the variances, right, for each one of the errors. E1, E2, and up to EK. Okay? Yeah. So minimize that equivalent to minimize this. As you can see, this is basically a summation of all the estimation errors, variance of the estimation errors. And that minimized equivalent to that P is minimized. Same thing. Okay? Yeah. Okay. Now let's get down to the basically the part of the mathematics now. Okay. So again, I'm going to write it here again. So minimize this P at here, which is E k plus 1. That's right. Okay. And then E transpose k plus 1. Okay. And let's write down the complete here. So this is x k plus 1 minus x hat k plus 1, and then x k plus 1 minus x hat k plus 1 transpose, right? Yeah, that's how you define your estimation errors. Okay. Yeah. Okay. So now the thing is, we have the x over k, right? This is from our system mathematical model, right? That's the x over k. We have it. We have this guy here. Okay, that's your x over k, right? Yeah. Now x hat should come out of this common filter model here, right? Yeah. So the question here is, what type of model should we use to generate this x hat, right? Yeah. So here is the model we're going to use here. So the model for the common here. So x hat, okay, x hat k plus 1 equal to gx hat k and plus h u of k, and then plus a small capital K at here, okay, and then c times x of k plus u of k minus c hat x of k. So that'll be our estimation model. Okay, that'll be our estimation model here. So if you look at the estimation model, okay, so let's break down to a little bit here. So first of all, look into the bracket here. So cx of k plus this is not u. This is a v at here. The sensor sensor noise v at here. Okay, this is what basically this is your y of k here, right? This is your y of k, and this one here is your y hat of k. Okay. As a matter of fact, when you see this one here, what does that remind you actually? The format at here. Yeah, the observer, right? That's the full order observer, exactly in the same format, isn't it, right? And if I don't have the v at here, that's the exact observer. In the k, in the observer, I use a letter L instead of a k at here. Okay, It's basically the observer type of model. However, the K at here, okay, now this time we call it the Kalman gain, okay, or Kalman filter gain. Okay, it's called a Kalman filter gain at here. If you have m number of outputs, okay, then the size of this K matrix is n by m. Okay, yeah. When you design the full order observer L, the L can be calculated using Kalman formula based on a selection of poles for the observer, right? Yeah. But this time, we're gonna calculate this K, right? Not like that anymore. We're gonna calculate the K based on the objective here, trying to minimize this guy. Okay. So that's basically different kind of perspective. End up with sort of a similar idea of observer gain, right? Okay. So let's take a look at how can I get this K at here. So we're going to get back to this minimization problem in here. So we minimize this. I have my original X, which is from the system, and I have the X hat now from this Kalman model, right? So all I need to do is I will, okay, write down the expression for X of K plus 1 minus X hat, okay, K plus 1. Okay. So what you do is very simple. You use the equation, write down the, maybe I'll write down here, equation number 1, okay, and then minus this equation number, let's call it equation number 3, right? So basically this is equation 1 minus equation 3. Okay. Now, so when you do this subtraction here, okay, so what it turned out to be is this. So gx at here, x of k plus w of k minus gx hat k, and then minus the g, the Kalman filter gain k, okay, times c x of k, and then minus Kalman filter gain k v of k plus c x hat k. Okay, so this is what you're going to get for the two subtraction, right, from 1 to 3. Okay, good. So now I'm going to group things a little bit here. Okay, I'm going to group all of the terms that has x of k. Okay, all of the term has x of k. And then you can also see here, see, if you group x of k here, this is g minus what, k times c, right? And if you group x hat here, what do you get? Minus bracket g minus k times c, right? So basically, the coefficient for xk and x hat k both are g minus k times c. Okay. Technically, this is a changing quantity, but I'll just write it down here. So k small k times c, and then x of k minus x hat of k. So that can be simplified to this. And then there are a few other terms remain here, which is the w of k and also this term in here. Okay, that is the estimation error. Okay, this is the estimation error. And technically speaking, and this at here is E of k. Now temporarily, okay, we're going to define these two terms. Okay, let's call it nk. Okay, let's call it nk here. Okay, and this nk, right? Essentially, you see that that's process noise and that's sensor noise, right? So the expected value for this noise should be what? 0, right? Okay, good. So now all I need to do next is remember the P matrix, right? Which is expected value here, here. Remember, right? Yeah. And this is basically what you do is here is the whole expression for E, right? This is the whole expression for the E at here. So you substitute over here and over here. Okay? Yeah. And I can write one more step at here. Basically, this is now this because E equal to, and if I substitute over here and over here, right? I'll temporarily skip writing of the steps for the small k at here. So we'll just write G minus KC. How about that? Okay. Yeah. And then this is E of k at here, and then plus N of k. Okay, that's one term, and the other term is G minus KC E of k plus NK transpose, right? Yeah. Yeah. So now the rest of the thing. So you when you have A plus B transpose, and that equal to what? Equal to A transpose plus B transpose, right? Yeah. So I can move the transpose into the into this bracket at here. Okay. So E transpose. Let's write down one more steps here. Okay, a couple more steps. So the first one you don't need to touch that. And the second one here, this is going to be a purely linear algebra operation. Right? So A plus B transpose equal to A transpose plus B transpose. And A is like A times B, right? That's another two terms here. So transpose of C times D is D transpose C transpose. So the first term becomes E transpose, and then G minus KC transpose plus this N transpose right here. Okay, so that's one more step right here. Okay, yeah. Sounds good? Yeah. Okay. Not too complicated actually. So now what you do is, okay, you will multiply basically this term with this term, that term with this term, this term with this term, you know, basically expand these two factors here, multiply them out. Okay, yeah. So when you multiply them out, and for example, right, if I use this term multiplied by this term at here, so what is that? That's basically this matrix multiply E transpose, and then multiply by this transpose here, right? Yeah. Now when you use, and then expected value of that term, okay? So expected that value of the term, this is a matrix G minus, that's not a random variable, right? That's a constant basically. And this is also constant, so you can take it out of that expected value expression. That makes sense? So basically for the expected value of this term multiplied by this term, that essentially equal to a G minus KC expected value E transpose, and then G minus KC transpose. That makes sense? Yeah. So we can do the same thing for the rest of the expansion here. So now let's imagine, right, what happens, let's say use this term minus multiplied by this N transpose at here, okay? And this is still a constant here, so that becomes G plus G minus KC expected value, this E at here, multiplied by N transpose, right? Okay. And then there will be a couple more terms. and then this term multiply that, so plus expected value n multiplied by E transpose, take out the G minus KC transpose, right? Yeah. Last one, n multiplied by n transpose okay, that's the full results of that expansion. Okay, yeah. So from here, right, if you take a look at this, the first one, what's this? This term here, expected E of K, E transpose K. What's this one here? P of K, exactly. Excellent. So this is basically P of K, right? Yeah. Okay, great. And then second one here, it's the E multiplied by N transpose. Well, what's E? E is the error, basically, right? And then N at here is defined as the white noise at here. Okay? Yeah. So these two, where is it? And these two at here, or even just these two at here. Okay? And you can prove that they are actually statistically independent. Okay? So basically means these two expected value should be 0. Okay? Yeah. And the last part, which is expected value of nk times n transpose, and n is over here, right? Over here, w and v. Okay? So you could substitute this n into here and here and do an n expansion, right? And then do this. So you can imagine, right? What happens when you use this one multiplied by its transpose? You're gonna get w multiplied by w transpose, right? You're also gonna get v multiplied by v transpose, and you're gonna get also w multiplied by v. But w, v are independent, right? So that expected value will be 0. So, but w times w transpose, its expected value, which is what? The not 0. W times w transpose, it's the covariance, right? It's covariance that is here. Okay, so essentially this term in here, you can prove it that easily. This is actually equal to the RW, okay, which is the covariance of the process noise, and plus the common filter gain K times the covariance matrix for the sensor noise, and then times the common filter gain K transpose. Okay. So overall, right, your original matrix, the covariance matrix for the error, which is we're trying to minimize. Yeah, we're not there yet, right? That covariance matrix can be expressed, right, simplified into what type of expression? So P of K plus 1 equal to G minus KC times P of K, G minus KC, and then plus this term in here, transposing here. So RW plus K, RV, and then K transpose. Okay? Yeah. So instead of having the expected value symbol, now it's like a difference equation now, right? It's a difference equation now. Okay. And this one here, okay, is essentially what we're going to manipulate now to try to obtain a minimum value for the P, okay, for the P at here. Okay. So, you know, when you see minimization problem, right, and it's always about what do you manipulate to minimize that quantity. That makes sense, right? So in this case here, what can we manipulate to minimize this P? K, right? So basically, can we find an optimal solution for the K such that this P is minimized? Okay. So basically, the P of K plus 1 here is a function of the K. So So what do we do? And what we do is very simple. Let's calculate the partial derivative of this p, and then set it equal to 0, right? So as every single like a simple optimization problem, you calculate the partial derivative and set equal to 0. Okay? And then you calculate the calculus solution, right? And that solution will give us for the k. Okay? Yeah. So set equal to 0 and solve for the k at here. Right? That's becoming this objective. Okay. So what do we do is, okay, so let's calculate then the partial derivative of this whole expression with respect to the k then, right? With respect to the k. Now we have to be careful a little bit. So the first term, you look at the first term here, right? Look at the first term here, which there are 1, 2, 3, all of different variables that are here. This is not a function of k, right? This is a function of k, right? And then p, this is a pk, this is not pk plus 1. So then partial p of k over partial k of k then should be 0. Okay? Yeah. So we're talking about partial p of k plus 1, right? Over kk here. And then you have a k at here and k at here, right? Yeah. So if I take a partial derivative of the first term with respect to the k, so it turned out to be this one basically. So partial like this, okay? If I call this is capital D here, for example, okay? So like capital D and P of k, and then D transpose and over partial k of k. Okay? So partial derivative, I use the chain rule. So calculate the variable D first, and then D with respect to the k, right? The chain rule. Okay? Yeah. And this first one, we did that actually in optimal control. This is basically typical matrix calculus, right? This is like a 1/2 mv squared, taking derivative with respect to the v, right? But it is just in the matrix format. So the first one give us 2d times p of k, because p of k is a symmetric matrix. So you get 2d times p of k. And second one here, what's the partial derivative d with respect? D is this one. And then it's like basically taking a first order derivative, taking order with respect to the k, you get negative c, right? But it's a scalar. But in this case here, because this is a matrix here, what you actually get a negative c transpose. Okay. Yeah. So that's the results for the first partial derivative, which is this one here. Okay. And the last one, this is a constant here, so that partial derivative back to the k will be 0. And the last one here is partial derivative k rv k transpose over k yeah. That's right. Right. So 2k rv. Okay, yeah, and equal to yeah, right. So you put these two together here, and let equal to 0. Okay, and d is the g minus kc, right? So I got what I get. The 2, you'll get rid of the 2, that's for sure, right? There's a negative in here, so negative 2 g minus kc plus multiplied by p of k times c transpose at here. Okay. And then plus this term in here, so 2 kk rv equal to 0. Okay. This term equal to 0, and my objective to solve for this k at here, right? So you can easily expand everything, put a k together, and then do an inverse. Then you solve for the k here. Okay? Yeah. So the k at here basically is equal to g times p of k c transpose at here, and then rv plus CPK C transpose inverse. Okay. So once you get this one here, so this basically the idea here is this is your common filter gain basically. See, right? This is the gain K in the common filter model. Where is it? Here, right? This is gain K for the common filter model here. Right? And that's how you calculate the gain K here. But the gain of K here, as appearance, it depends on what? It depends on this capital P, right? Depends on capital P. Okay. So what we need to do is we need to substitute this K at here, okay, basically back into that original capital P K plus 1. Okay. And then by substitution back into this, and this I'll skip a few steps now, so this P of K plus 1 can be simplified into the next expression. Okay, which is this. So now these two equations together, right? Then you will be able to calculate the P and also the K here. Okay. And the typical process for doing this calculation is you will start with P0, okay, which is P naught value. Okay. You start from here, calculate this P1, substitute, and then you get the K1. Right? So then everything iteratively, you get the solution right here. And this is these two equations together here, okay? And this is called prediction type common filter. Okay, prediction type. And just like the name for the full order observer, right? That's called prediction type observer. Right? The same idea, right? Same thing. Okay. Now, in the actual implementation, we actually will not use the prediction type. We actually will use just like observer. What's the next for full order observer? What's the next type of observer? Remember we learned reduced. But then after reduced, there's another one which is called current, right? So we extend this one slightly. We'll extend it to the current type of common filter, and the results of that will be for our implementation in here. Okay. Yeah. So just to jog your mind, essentially, what's the current? This is part. I'll skip quite a few here. So current type common filter. And if you look at the writing I gave it to you now, you will see this is essentially the same kind of a notation or the structure as the current type of observer here. Okay? Okay, so this is the model for the current type common filter. Okay, so let's take a look. So don't be scared. Oh, look what's going on here within the bracket here, right? Now let's back off a little bit here. Okay, let's back off a little bit in terms of the prediction type. So you see the prediction type, I have x hat k plus 1, right? Yeah. Now technically I could write it actually like this. So k plus 1 and then vertical line and the k. Okay. So what this means is, I'm not sure if you remember, when we do the review there's one type of probability is what? Right? A on the condition of B. Okay? Yeah. And basically, using very simple language is, if you know B, then how do I predict A? Right? Yeah. And then prediction, for this type of prediction here, if you look at this prediction here, this is essentially what prediction means, right? All the k plus 1 value is predicted based on the past k value here, right? Yeah. And this observer deriving at here. So the first row at here, that's very much like the system matrix G and H here, right? The system model here. So this portion is called prediction. So you're predicting the X, okay, based on the past, okay, based on the past information. And then the second step at here, this is basically called an update. Okay? So then you update the first predicted one with this term, right? And that term is the multiplication of the common filter gain with the difference between the actual output and the estimated output. Okay? But this is the current, you compare the value here, the k plus 1, that's both are current steps, right? Both are current steps. So you're using the current feedback to update the prediction or estimation. And that's exactly the same structure as the current type of observer, basically. Okay. Yeah. So what do you do next is essentially same idea. You'll try to what we're trying to do is minimize p of k plus 1 and k plus 1. Okay, because this is the notation wise is slightly different, right, from the previous observer design or common filter design. Okay, and this is expected value. Okay, and E of k plus 1, and E transpose k plus 1. Okay. Still, where we're trying to minimize this, and the E at here, okay, is this one I don't need to. This is basically the current value for the state minus the estimation. Okay, k plus 1, k plus 1. So basically this term here. Okay, yeah. No difference from the previous objective, right? You're trying to minimize the covariance matrix and error matrix. The estimation error is the actual state minus the estimation state, okay, out of this current type of common filter at here. Okay. So you can imagine what's going to happen, which I will not write, right? You have the expression for this, you have the expression from here, so you put things together, right? You do partial derivative, and then you start to calculate the k, right, basically, right? Yeah. And then the results basically is one-page handout I gave it to you in the previous lecture. The results, what you get, okay. Here, right? This is the results what you get here. So your gain k will be this one, okay? And then there's kind of different steps trying to implement this current type of common filter here. Now technically, as you can see, in terms of implementation, 1, 2, 3, 4, 5. So 5 lines of code basically, right? So all you need is just 5 lines of code in order to implement this current type of common filter. Okay. So it's not too bad actually. And there's one example here which I will also go over using a Simulink with you guys. Okay, so for example, I'll show you the example here. Okay, here's the double integrator, right? This is a double integrator. We did that many times, and that can be discretized into a state space model, which is this one and here. Okay, and it has a matrix G and H. Okay, like this. Suppose in this time we'll take a sampling time of 0.01. Okay, yeah, and we do have a process noise and also the sensor noise at here. So in this case, there's only one output, so the sensor noise actually just the scalar quantity at here. It's not a vector, right? Process noise, we have a sort of vector at here. That vector essentially what it does is, you see what it does is basically saying is the first state has no noise, right? And the second state has a noise at here. Okay, that's basically what this one does. So when you have a matrix in front of W at here, there's a slight difference, okay, in terms of that in the calculation results here. So the W in front of W, you need the additional matrix, okay, for calculation. Okay. Okay, so and then what you do is you can implement the common filter here. Let's see, in this here we're implementing common filter for the just calculating the common gain in this case. Okay, you see how it's being implemented is actually 3 line of code. You could combine the code into 3 line of code here. Okay, so you can estimate. I'll show you here. So in the handout, there's another shortened version of the common filter right here. Okay, so you can implement this one. It's equivalent to the top. Okay, so what I did is basically calculate this, and then calculate common filter again, and then calculate the P again. Okay, substitute the P back here, calculate M, and then substitute M, calculate common filter again here. Okay, so that iterative process, okay, will calculate the common filter again. Okay, and as you plot the common filter gain out, you will see in this case the system is a 2x2 system, so the order is 2. And so the common filter gains, and then there's only one output. The size of the common filter matrix is what? It's 2 by 1, right? So there's vector 2 by 1. And when you plot it, so there basically, I plot this according to 3 different scenarios. Okay, one scenario is essentially when the process noise ratio over the sensor noise ratio is 1. The other one is when process noise over the measurement noise ratio is 2. Okay, and then there are 2 common filter gain basically. Basically your K, right, equal to this is K1 here and then K2 at here. Okay, so that's your common filter 2 gain, right? So we're plotting both of them basically. Okay, we plot this value or plot this value here. Okay. As you can see, this is K1 I believe, and this is probably K2. Okay, so as you can see, both of them will actually eventually settle down, right, to a constant value. So which basically means the common filter gain, okay, given a few steps, it will settle down at a constant matrix or vector. Okay, yeah. And that's actually the next one. I'll just quickly go basically what's the steady state common filter design, right? And just like our steady state optimal control, right? Yeah, the optimal gains also kind of take a few steps to settle down, isn't it, right? Yeah. But I do want to create a very simple sort of intuitive understanding at it here. Okay, so I know that you need some time to digest for sure, right? But let's take a look at the simulation here. Okay, so what I did, as I said, I considered 3 different ratios, right? 3 different ratios here. So first of all, I want you to understand the difference, okay, between the ratios here. So here is ratio between RW and RV, 1 to 3. Okay. So what's RW again? Process noise covariance, right? And RV is the process, it's a measurement noise covariance. Okay, yeah. So if I have RW over RV equal to 1, basically means what? I'm assuming the process noise, the variance, are approximately the same as the measurement noise or the sensor noise, right? Okay. Now, if the ratio increases, let's say even not 3, let's say even 10 or more, right? And what does that mean when this is a bigger number? Which noise has more variance now, if this bigger number? Yeah, so if this is a bigger number, meaning RW must be bigger, right? So basically, the process noise will have bigger variance now, right? Bigger noise, basically, if this number is big. Is that good? Or if this number is small, that essentially means I could if this is 0.1 or 0.01, okay, that basically I can see is the sensor noise tends to have more variance or a bigger basically noise than the process noise, right? Okay. Okay, so understand the difference now between RW, RV now. Okay, so let's go back to the common filter at here, right? Go back to the common filter. So if you look at the common filter here, right? So common filter, basically you have estimation here equal to this plus the common filter gain multiplied by the difference at here, right? Multiplied by difference. And the difference for this difference, what's the difference here? Difference is it's the actual system output minus the what? The estimation outputs, right? The common filter estimation outputs. System output, in other words, equivalent words, system output basically what output? What type of output? Where is the system output from? Where do you get the system output? Pardon me? Right? Where do you get here the system? Well, how do I get the system output? From what? From what type of a device? Sensor. So this is basically from sensor here, right? So this guy here is basically from the sensor here, and then you're using the common filter gain multiplied by the difference at here. Okay, does that make sense? Okay. So now you think about the scenario here, right? If your system sensor has a lot of noise, okay? A lot of noise basically means you measure the sensor, all you get is what? Noise, right? You can't even tell what's inside buried underneath the noise at here. Does that make sense? Right? Now, as a designer, right? Forget about common filter. As a designer, right? So you're required to use a gain at here to multiply by this difference, right? What do you think about the gain? Would you choose a bigger gain or would you choose a smaller gain? Smaller, right? Because why do you choose a smaller? Because you know this is so noisy, and I don't want to multiply the noise again by multiplying another value at it here. That makes sense, right? So if you look at the simulation results at it here, actually, as I just said, when this number is smaller, it actually refer to what? To refer to the situation when RV, when this, sorry, when the sensor noise is big, means RV is big, right? And that means the ratio will be smaller. So, and that means you see here, which one has actually smaller gain in here? When this is smaller, 1 here. This has a basically smallest common filter gain in here, isn't it? Right? That's exactly the intuition that you actually wanted to do, basically. So when your sensor noise is big, what you do is, or what the common filter will give you is, you will give you a smaller common filter gain, basically. Okay. So how about the other way around? Let's say the other way around is, so let's say what you do know is, you know the sensor actually pretty good, okay? It generates fairly clean signal. Okay? But you know there are maybe relatively higher process noise in the system. So that will give you basically what? Higher ratio at here, right? Okay? So now you come to the common filter design at here. You have a gain at here, and you have a difference. This is a sensor output minus that common filter estimation output here. So basically, if you're confident that your sensor actually is generating clean, good signal, then you must be confident also to do what? Okay, I can apply relatively bigger gain K at here, right? Yeah. So the K at here is more or less like what? It's more or less like a control effort, right? So if you want to control a system, and if you control it fast, what do? You must have to give it a bigger control effort into the system here, right? So that's exactly the same kind of a trend that you're trying to follow at here, essentially. Okay? Yeah. Now, when we do our simulation, we're going to be able basically to observe that as we manipulate manually about the sensor noise variance. Okay, and then we'll observe basically what's the difference here. But I want you to understand the effect, okay, the effect of the two ratios that are here in terms of the common filter gain. Okay, yeah. And I typically actually will test a very simple concept type question in the final, just like this, right? It's very simple ones. Okay. Okay. So let me finish maybe just the theory part, and then we can get on the math lab next week together here. Okay. Yeah. So there is only one simple concept here. Basically, it's called steady state common filter. Okay, steady state common filter, and we're looking for basically an expression, okay, for steady state common filter. Steady state common filter basically means your common filter gain K will approach a certain constant as this K goes to infinite. Okay. Same thing, that P matrix will actually also go to a constant P at here as K goes to infinite. Okay. So that covariance matrix P will also basically go to a constant value. Okay. And then and how we can do is we can actually simply make use of the results from our prediction type of a common filter. Okay. So prediction type results is, it's these two formulas, right? It's these two. Okay. Yeah. So all we need to do is basically we're gonna get rid of the K's, because they are going to be constant now, right? And then leave all the K out, okay? Yeah. And that basically become a steady state common filter here. So that'll give us the following two equations. So K equal to P times C transpose, and RV CP C transpose inverse, and P equal to RW plus G PG transpose GPC transpose RV CPC transpose inverse CPG transpose. Okay, so a little bit longer expression. So we'll get an expression like this essentially. Good. So I'll give an example here. Basically a simple example. Let's make use of this to calculate the capital K and the capital P at here, right? Yeah. So let's take a look at the very quick little example here. Let's consider a very simple system, which is actually a scalar system. And that's the system we have been dealing with, but in this case it's a very simple scalar system. As you can see, basically this is our G matrix, and H matrix, which is 1, right? And then C matrix, which is 1 over there too. Okay. So I can write down G matrix equal to 0.5, and H is 1, and C is also 1. Okay. So let's say, suppose that the process noise has a variance of 0.5. So RW, let's see, is 0.5. And then the sensor noise, let's see, has a variance of 2. Okay. Okay, so then let's calculate basically what is the P and the K equal to at steady state. Okay. Now there's only one. Sometimes I do trick in a question. I may trick you. Very simple trick. The question maybe give you a description. The process has a standard deviation of 2. So then what's RW? No, has a standard deviation of 2. Then RW equal to variance equal to variance equal to the power of standard deviation, right? Yeah. So if I tell you the noise has a standard deviation of 2, then the variance is 4. Okay? Yeah. Huh? Am I right? Yeah? Yeah. Variance is sigma square, right? Yeah. Standard deviation is sigma. Okay. Anyway, so let's basically make use of these two equations here. So first I'll do is I'll calculate the P, and then substitute P back over here, and then we'll get the K value here. Okay? Yeah. So P equal to RW plus that long expression, so GPG transpose minus GPC transpose, and RV plus CPC transpose inverse CPG transpose. And then RW is 0.5, G is 0.5, and G is 0.5, C is 1, RV is 2, C is 1, inverse 1, G is 0.5, right? So that's how you substitute all the relevant numbers into that expression. Okay. Then you simplify it a little bit. So 0.5 plus 0.25 times P, and here is 0.25 times P squared divided by 2 plus P. Okay. So multiply the 2 plus P, okay, out of here, so you get P squared plus P minus 1 equal to 0. And then you get to solve this. You get two numbers. One is positive, and one is a negative. Okay. So you take what? The positive, huh? Yeah. Because P is basically a positive semi-definite matrix. Okay, it should be. Yeah. And that's how you get the P. Once you get the P, then you can calculate the K, which is K equal to PC transpose RV CPC transpose inverse equal to P over P plus 2, so 0.2361. Okay. That's what MATLAB will give you. So if you use the MATLAB, good point. So if you use the MATLAB, then here is the command. You can use this so-called DLQE to help you with the MATLAB. Okay. So DLQE, how you use this is this. I will write down just temperatures. This is G matrix, and this is H, and then this is W at here. Right? Okay? Yeah. So when you use the MATLAB, you use DLQE, okay, and then plugging the G at here, and then plugging a unit matrix I. So this unit matrix I it's basically, this is like 1 0 0 1 and here, okay, yeah. And that I essentially, if this is other than this, then you have a different basically. Okay, so GI, and then plugging the next one, the C output matrix, and then the variance for the process, and also for the sensor. Okay, yeah. That's how you can use DLQE to calculate the common filter gain K. So for example, in this particular simple example, we should plug in what? 0.5 at here, and I is 1, C is 1, this is 0.5, this is 2. Okay? You can use a MATLAB, then you get exactly the same thing. Okay? Yeah. Is that clear? Yeah. So next lecture, I'm gonna go over the Simulink with you guys, right? And we'll be able to hopefully we can finish in one lecture. So bring your computer here with you, okay? Yeah. Now, I do have a couple minutes at here, but I do want to quickly just go over the last topic, LQG. Okay. So, very simple actually. LQG is called the linear quadratic Gaussian control. What it does essentially, what you do is you combine the common filter and optimal control together, then you get LQG. Okay, yeah. So if you look at this diagram here, there's nothing new now, right? You use the common filter to observe the state, and you use optimal control K to generate the control input, and then that's it, right? In the similar scenario previously, what do we use for the common filter? We use what? Observer, right? And what do we use at here? We use the pole placement to generate the K here, right? Yeah. So completely same structure. It just deal with a slightly different situation. Here is basically you have a noise in the system, essentially. Okay. Yeah. Actually, this morning one of the group showed me when he was using observer plus the pole placement for the control, for observing and also control, and he noticed that the output system sort of have a little bit jitterings all the way in the output here, right? Yeah. Now, one of the reasons could be is, say when you design an observer, your observer is based on what? Based on the mathematical model, isn't it, right? Which is the model I'll give it to you. Okay. So when you do the simulation, perfect. Everything actually you should observe things perfectly, right? Yeah. But when you bring the simulation to the experiment and you apply the observer to the experimental model, what's the difference now? There's a mathematical model, there's the experimental model. These two always have a difference, right? Always have a difference. Okay? So your observer works perfectly for the mathematical model, but doesn't necessarily work perfectly for the actual model here, right? But then if you generate your control actually based on the estimation, so if the estimation is not accurate, then there will be certain type of basically behavior, right, in the control system outputs. Okay, yeah. So that's the difference here. Okay, yeah, and that's actually what I really want you to get, from the actual experiment and the simulation here. Simulation is always perfect, right? But when then you implement, and you always notice some difference, and that's basically what you really want to observe it here. Okay. Yeah. So anyway, I think I can stop it here. And you do have a few minutes. If you don't mind, you can do the teaching evaluation. And I'll remind you guys in the next lecture. Okay.
for matrix calculus?
Just a sec.
Okay.
Let me stop this.